Hello and welcome to CE 3105 Mechanics of Fluids Lab at Texas Tech University. And in this video, I'm going to talk about friction losses experiment that we're going to conduct in our lab this week. So friction losses are also referred to as major losses, and they are a very important component in water supply and wastewater treatment designs because we use pipe networks that often extend tens to hundreds of miles to move water either from a source to a treatment plant and from there to consumers. And at the same time, we take water from households or the wastewater from our households, move them to treatment plants, and then eventually to natural water bodies. In addition, when there is rain, we take stormwater, we collect stormwater and move them either to a treatment plant or discharge them to a surface water body. So in all of these instances, we use pipes. So understanding how water flows through pipes and the energy required to move water from a point A to point B is of great interest to civil engineers designing water supply systems or in wastewater systems and stormwater systems for cities. Um, as water moves through the pipe, it encounters frictional resistance. So we all know that right at the wall of the pipe, the velocity of the water is close to zero. This is called the no-slip boundary condition. And the maximum flow occurs almost at the center of the pipe, where the frictional resistance is the least. So what we have in a pipe is a velocity profile where the velocity goes from zero near the walls of the pipe all the way to a maximum velocity. So we typically don't measure these velocities inside the pipe, but we use an average velocity called V, and we say that is equal to the flow rate over the cross-sectional area. Clearly, the greater the flow rate, the more the velocity, and similarly, smaller the cross-sectional area, the smaller the velocity. So the V is equal to Q over A is your continuity equation. And we can write Bernoullis equation, which is a statement of conservation of energy by adding a friction loss term. So now if I look at a pipe and I take 2 points on the pipe, point A and point B. At point A, the pressure in that pipe is given as P sub A. So the pressure head is PA over gamma. Similarly, the velocity is V or V sub A, and V sub A squared over 2G gives me the velocity head. And then ZA is the potential head, or the energy due to the location of the pipe or the height of that pipe from an assumed atom. Similarly, at B, I can write my pressure term, the pressure head term, the velocity head term, and the potential head or the elevation head term. And because some energy is lost, the total energy at point A is equal to the pressure, velocity, and potential heads at point B plus head loss term, or this represents the loss due to friction. Okay. So what we are interested in is calculating the head loss term. And clearly, if I know the remaining terms, I can calculate what that head loss term is. So let's take a deeper look at that head loss term and see what it actually depends on. And head loss due to friction depends on three characteristics. Okay, clearly, the longer the pipe, the greater is the head loss. So if I were to move water over a kilometer, I'm going to experience a greater head loss than moving the water, say, over half a kilometer. So that is intuitively obvious because the water has come into greater contact with the pipe, which causes frictional resistance. The head loss is also proportional to the kinetic head. So obviously, the greater the velocity with which the water is moving, the more is the chance for that water to be in contact with pipe walls, and also there is turbulence, which causes energy loss. So the total head loss, so the head loss is proportional to the velocity head of the V squared over 2G. And similarly, the smaller the pipe diameter, the greater the head loss. This is also intuitively obvious because if I have a smaller diameter pipe and everything else stays the same, the water is in greater contact with the pipe walls, which causes frictional resistance. So the friction is proportional to the length, proportional to the velocity head, and inversely proportional to the diameter of the pipe. The Darcy-Weisbach equation essentially takes all these terms and puts it together and says that the head loss is equal to FLV squared over 2GD. Again, L is the length of the pipe, D is the diameter of the pipe, and V squared over 2G is the kinetic energy head. So it also introduces this term called the friction factor. And the friction factor depends not only on the flow regime, but also on the pipe material characteristics or the surface roughness of the pipe, because clearly not all materials are the same. And as a result, a material that has greater roughness will provide greater frictional resistance, and the material and a pipe made out of a material that is smoother offers less frictional resistance. So, as I said, the frictional resistance depends on flow regimes or the velocity with which the water flows. So, we define our flow regimes in fluid mechanics using a concept known as Reynolds number. And the Reynolds number basically represents the ratio of the inertial forces to the viscous forces. The inertial forces causes the water in the pipe to keep moving, and the viscous forces is the resistance offered to that movement. So Reynolds number can be calculated using density, velocity, diameter, as well as the dynamic viscosity. So Reynolds number is given as rho v d over mu, and d is the characteristic length, and which is usually taken as the inside pipe diameter in pipes. And for laminar flows, we say in pipes we have laminar flow when the Reynolds number is less than 2,000, and we say turbulent flow when Reynolds number is greater than 4,000. And somewhere between these two Reynolds numbers, we encounter, transition flows or critical flows, where the flow actually exhibits both laminar and turbulent characteristics. So what's laminar flow? Well, when water moves at low velocities, water molecules tend to move in a smooth, orderly manner, and water parcels in a pipe can be envisioned to be moving in parallel straight lines. So there is least amount of resistance to that flow. Turbulent flow, on the other hand, it happens when the velocities are very high, and that causes the water movement to be disorderly, and it also creates the formation of vortices. So you must have seen this diagram or the Moodys diagram in your fluid mechanics class. And basically what the Moodys diagram basically tells us that it plots friction factor on one side. Again, this friction factor is the Darcy-Weisbach equation, and it plots Reynolds number on the x-axis, and it also plots the surface roughness on the y-axis. So each of these curve belongs to different surface roughness that is shown here, or the relative roughness. The relative roughness is the absolute surface roughness, which is given by this epsilon divided by the pipe diameter. And I present here the absolute roughness for a variety of different pipes. As you can see, galvanized iron pipe has more roughness, or the cast iron pipe has, or an uncoated cast iron pipe has very high roughness, followed by galvanized iron, followed by cast iron, so on and so forth. And of course, if you have a glass pipe or a plastic pipe, the roughness, the internal surface is very smooth, so you will have less absolute roughness. Okay, so here the friction factor under the laminar flow regime, so that's 1,000, so it stops at 2,000, goes a little bit to about 2,300 or so, and so is inversely proportional. The friction factor is inversely proportional to the Reynolds number. Basically, what that means is that the more viscous the fluid is, the less is that friction, and also that the head loss is, under laminar flow conditions, the head loss is proportional to the velocity. In the turbulent flow conditions, you will see that nonlinear profile. So the velocity, so head loss is proportional to the square of the velocity, and it also depends on the surface roughness. So with that theory in mind, what we did in this experiment, or what we do in this experiment, is we run this experiment for two conditions: the laminar flow conditions and transition or turbulent flow conditions, or low velocities and high velocities. And to get low velocities, we make use of a top reservoir where we fill it up with water and move the water slowly into our apparatus. And our apparatus essentially has an inflow which is regulated, And as the water comes in, the water moves through a pipe. Remember, see that we have made that pipe really, really small because we want to be able to measure significant friction losses over a very small distance. So we give you the length of the pipe, we give you the diameter of the pipe, and then we use the manometer to calculate the pressure differences for various inflows. And of course, we use a volumetric measurement. So we collect a known volume of water over a given period of time and measure the outflow. So we repeat this step several times to make sure that you get the pipe length and the pipe diameter from before you leave the slab, and then have your data sheet attested by the TA. So similarly, the turbulent condition, the experiment is exactly the same, except that instead of using an overhead tank, we directly make use of the flow from the hydraulic bench to set the flow so that we get higher flow rates. And also, instead of using these manometer, we make use of a pressure gauge to directly measure our flows, either in PSIs or in meters of water. So you may end up measuring either the pressure head or the pressure. So make sure you put in the appropriate corrections depending on what you use the measurements or the units of that measurement. So key factor, again, keep track of the units in which you are making your measurements, and keep track of the units in which you are making the calculations, and apply appropriate conversion factors as necessary. Uh, so at the end of the experiment, you probably got an idea of how friction losses, why friction losses are important. So why do we have friction losses in pipes? What factors control friction losses in a pipe? You also need to know Darcy-Weisbach equation, how to use it, and how is it useful to calculate frictional head loss. What does the friction factor of a pipe depend on? So we talked about Moody's diagram, the absolute roughness, the surface roughness, the Reynolds number, and how Darcy-Weisbach equation, the friction factor coming out of the Darcy-Weisbach equation, relates to all of this. And what role does the flow regime play on friction losses? So how does the friction factor change when we have laminar flow versus turbulent flow? And more importantly, as civil engineers, you need to know where this concept comes in handy, particularly in the design of water supply systems. So those are the key concepts that you need to know as part of this experiment. So I hope this video will help you refresh what we did in the lab and give you a good starting point to write your lab reports and make all the necessary calculations associated with that report. All right, thanks.